Hello Senior Design 2016. Our group was Team MOBO, which stands for Mono Board. Our team consisted of Chase Pruitt, Cody Vorgert, Zach Gutowski, and Dustin Delk. The purpose of our project was to develop a fun and effective personal form of transportation which could replace the current craze of hoverboards.
So this is our board, and we try to figure out the electronics of it. Obviously, to start with, we need to figure out how big of a motor we needed to propel a human adult, and also how we're going to then power that motor in order to keep that adult moving. We decided on this 450 watt motor after talking with Professor Dempsey, thank you. After talking to Professor Dempsey, I'm horrible with names. And he told us it was plenty large enough motor, given the voltage he was using in the past. He could have a motorized bicycle with an adult 25 to 30 miles an hour, using a little more voltage than what we were going to use. We decided to use 24 volts versus a potential 30 to 36 volts. That enabled us to use a speed controller that was more manageable in price. Also, when we try to find batteries to suit our needs, using 12 volt batteries that we have, if we went with 36 volts, we would need 3 of them to try and fit 3 batteries on this board wasn't possible. So due to lack of space, we chose 2 batteries, and we went with the lithium-ion, or we went with the lead-acid batteries instead of lithium-ion batteries because, one, the lithium-ion batteries, while they would have worked great for application size-wise, they were much too expensive for what we needed in order to deliver the proper amount of amperage for this motor. The lead-acid batteries like we have gave us the amount of amperage we needed to deliver all the wattage to the motor for full speed operation, but the trade-off is they're ginormous, but they fit within our budget. That was one of the hassles or obstacles we had to overcome, is trying to get these heavy 10.5 amp hour 12 volt batteries. There's one here and there's another one under this route to fit on the board. For charging purposes, they're normal lead acid 12 volt batteries, just like what you use in your car, so we can still use a car charger for them. So at least that made it convenient. We didn't have to have a special charger like we would with a lithium-ion battery. The motor that we selected has the motor inside, and it has a gear reduction inside to then have an ultimate output speed slow enough that we can hook up a normal bicycle chain gear set to it for our use. If this was just a motor by itself, it would turn around, say, 2,500 RPMs, or even 3,000, depending on what the motor was. But because it has that built-in gear reduction, the output of this flyover, the pinion gear, maxed out 500 RPMs, give or take. So then we're able to use normal gear reduction in a chain to bring our wheel speed down to a proper level, so we're not going 20, 30 miles an hour. It also, because of all the gear reduction, acts as a torque multiplier, so we can actually move a full-size adult up or downhill, flat ground, etc.
So this video shows the basic concept of our project using a small motor controller and a small toy motor. As you can see, depending on which way and how much you tilt the gyroscope, the motor controller will send the appropriate amount of voltage to the motor. In this clip, we have taken the concepts from our previous video and connected everything to our actual components. We also added a kill switch which will stop the motor from running if there is no pressure on it. Instead of our batteries, we connected the motor controller to the power supply with a little over 5 volts. The following images will give an idea of some of the mechanics involved in our project. This image shows the sprocket, which we had welded to a sheet of metal, which was then bolted to the hub of our wheel. Our axle was connected to the board using 3 metal clasps, which were screwed through the metal pipe into a metal sheet and through the board. The first configuration for mounting the motor involved 2 metal L brackets, which were screwed directly into the motor's previous screw holes. This picture shows an overhead view of these components. This clip shows the speedometer function of the board. The speedometer used a Hall effect sensor which was attached to the board and a magnet which was attached to the gear. Using a timing mechanism in the Arduino, it was coded to calculate the miles per hour based on the circumference of the wheel and how often the Hall effect sensor sensed the magnet. This clip shows what the speedometer looks like when it's finally connected to the board. Since our original pressure pad broke, we were forced to use the black button shown as our new kill switch. When it is not pressed, the wheel will not turn. It also demonstrates the implementation of the LEDs to come on depending what way the board is tilted. Since the Arduino can only output 5 volts and the LEDs need about 12 to become visible, we used a circuit similar to the one shown using the LM277.
Alright, so probably just have them go turn.
There we do have the speedometer working.
You needed to let go when you had it.
A little bit.
Yeah. You made it like
2
Like
tiles.
4 fouls. The problem is you like,
You try
yeah, you want to like lift your.
In the end, wheel diameter proved to be a pretty big factor. I believe if we had an extra few inches of clearance and smaller batteries, we could greatly improve the functionality. We tried to adjust code quite a few times to adjust for initial jolt of the start, but no matter what we tried, it proved too hard to ride. Alternative motors such as an id-hub motor or a belt instead of a chain could be used to improve functionality. With greater time and resources, I believe we could make the necessary adjustments to make the board more rideable.